Right now, your phone can look at millions of possible routes across a city and hand you the fastest one in about 20 milliseconds. It doesn't check them all. It uses one idea, invented in 1956, that still runs inside almost every map, every router, and every game world you touch. This is Dijkstra's algorithm, and by the end of this video, you'll be able to run it by hand. Here's the thing, beginners get wrong first. The shortest path is not the one with the fewest turns. Take two routes to the same place. One has 3 hops, but those hops are long and slow, and it takes 41 minutes. The other has 4 hops, and it takes 26. Fewer steps lost. So we stop counting steps, and we start adding up weights. A weight is just a number on a connection. Minutes, miles, dollars, whatever you care about. So here's our map. 6 places, labeled A through F, and 9 roads between them, each with a cost. We're standing at A, and we want the cheapest way to reach every single one of the others. Not just one destination, all of them. Dijkstra needs only 3 things. First, a distance table. Every place starts at infinity because we haven't found any way there yet. And our starting point, A, starts at 0. Second, a visited set. Once we lock in a place, we never touch it again. And third, the greedy move. Always go to the closest place you haven't visited yet. And there's exactly one operation you repeat. It's called relaxation, and it's just a comparison. Take where you are, add the cost of the road, and ask, is that cheaper than the best price I've seen for the place at the other end? If yes, write down the new number. If no, leave it alone. That's it. That's the whole algorithm. Watch it run. We start at A with 0 and we look at its neighbors. B becomes 4, D becomes 1, E becomes 7. Now, greedy move. The closest unvisited place is D at 1, so we go there and lock it in. From D, we try B. 1 plus 5 is 6, but B is already 4, so we keep 4. We reach C at 9, we improve E from 7 down to 3, and we reach F at 7. Closest unvisited is now E at 3. And here's the payoff. From E, F costs just 1 more, so F drops from 7 to 4. Then B at 4 gives us a better route to C, bringing it from 9 down to 6. F and C add nothing new, because everything around them is already locked. And we're done. 6 places, 6 shortest paths, and every one of them is guaranteed correct. How fast is it? That depends entirely on how you find the closest node each round. Scan a plain list every time and it's slow. Use a priority queue, a structure that always hands you the smallest item first, and you get order of V plus E log V. In plain English, it scales beautifully, even to a whole city. That's why it's everywhere. Turn by turn navigation. Internet routing protocols deciding how your data crosses the world. Game characters finding their way around walls. Delivery vans planning their next stop. One warning though, Dijkstra only works when every weight is 0 or positive. Give it a negative edge and it breaks. It locks in an answer before that negative shortcut ever gets considered. And it will confidently give you the wrong number. If you have negative weights, reach for Bellman Ford instead. And that's it. You now understand the algorithm that quietly routes the modern world. Next up, we take this exact idea and make it smarter with A*STAR search. Subscribe, and I'll see you in the next one.